Welcome. Hello everyone. Welcome to today's HAO colloquium. Today our speaker is Hongyang Luo from the University of Hong Kong. Hongyang is a PhD candidate at the Department of Earth and Planetary Sciences, University of Hong Kong. His research interests lie primarily in theoretical and computational space plasma physics, including planetary magnetosphere and solar physics. He is visiting HAO as a Newkirk Fellow and is now working with Dr. Yuhong Fan on the development of the magnetic flux eruption code for MHD simulations of corona mass ejection initiation. And today, Hongyang will be talking about the Yin-Yang MFE code, recent extensions and applications. Please go ahead, Hongyang.
Yeah, thanks. So I'll be talking about Yin-Yang MFE code and some recent extension and some applications. So quick outline. I'll be briefly talking about the MFE image model first, and then the first extension and some application of the usage of high order methods, and also the second extension of implementation of the full sphere simulations using the Yin-Yang overset grid. So here's a comparison of several well-established methods of numerically modeling of the space and actual plasma. On the right side, we have the particle or the kinetic models, so which provide the electron scale of particle physics. But the disadvantage of it is it's really expensive, and most of the time it's restricted to the modeling of plasma in a really tiny region. And on the left side, we have the MHE model, which provide a large-scale fluid physics. And most of the time, it's a favorable one because the cost is affordable and generally it provide a pretty good description of the system most of the time. And we also have the hybrid is in the somewhere between that provide ion scale ion physics. Yeah, but generally speaking, it's still a lot more expensive than the magnetohydrodynamic methods. So this plot actually shows that MHE is not always the best choice for modeling the space and actual plasma, especially when the DI or the gyro radius is comparable with the scale length of the system. But what if for the solar wind and for the CME simulations, actually the scale length of the solar wind and CME is around above a megameter, but then the DI or the gyro radius are not above 100 meters, several hundred meters, which means that it's on the far top left corners, means the MHE modeling is very suitable for this kind of distance. I'll introduce the numerical MHE model we're using, the so-called magnetic flux eruption MFE code. That's been used for quite a long time. And here we show several. Okay, I don't know why the movie is a little bit not clear, but okay. Hopefully it's clear online, but okay, yeah. So we show it has been used for the modeling of emergence of a Twix flux tube from the interior into the corona due to magnetic buoyancy instability. And also we have used MFE code for modeling the CME events. On the right side, and more recently we allow the usage of a data-driven inner boundary condition for simulation of CME events. So this is the equation set we are solving. So basically, we are solving the single fluid ideal MHD equations. We have the continuity equation, the mass equation, and the momentum equation, the Faraday's law, the divergence be equal to 0 constraint and also the internal energy equations. And the electric field is determined according to the ideal Ohm's law. And we also include also called semi-relativistic corrections, accounting for the low beta region where the alpha speed can reach the same magnitude or even higher than the speed of the light. So it has all those realistic physics, including the electron heat conduction. We use a hyperbolic method, similar to what is used in the Moran code. And also we have the include the optically thin radiative cooling and empirical corona heating. And by using the MFE code, we can solve the equations, MFE equations in the Cartesian or spherical geometry. And we recently include the usage of the high order reconstruction method and modify Friedrichs flux, numerical flux, in also similar to the one used in the Moran codes. So basically, we reduce the numerical diffusion by using such a modified flux, multiplying a prefactor to the diffusion speed in the numerical flux according to the smoothness of the profile. So if the profile is smooth, then we reduce the numerical diffusion. But if the profile is non-smooth, we keep the numerical flux as a very diffusive original localized Friedrichs flux. We also use the constraint transform method. So we ensure the divergence of B is 0 to the machine position. We include the semi-relativistic corrections. And we also have the yin-yang grid for the axis singularity, allow us to perform the full sphere global simulations. And we use the NCAR for the parallelization.
Will you explain what that grid is to us?
Yeah.
Good. Thank you.
Yeah, so the way we solve the equation is very important and actually affects the solution quite much. So one well-known issue for solving the MFE equation is the diff-V problem. So without special care, you cannot guarantee that the diff-V is 0 all the time. And if you allow a non-zero diff-V and use a conservative form of the Lorentz force, basically you get a field-aligned acceleration along the field lines. So, and the magnitude of the acceleration is proportional to the strength of the magnetic field, which means that it will cause a trouble for low beta region, where the magnetic field is so strong, and you get a very inaccurate field-aligned acceleration, and sometimes it just causes the code to crash. So the way we deal with the diff-V problem is we use a scatter grid. We define the velocity and the magnetic field on the cell physics, while the rho and the internal energy E are defined on the zone centers. Also, we define the electric field on the cell edges. So by using such a stagger grid, basically we are using the Gauss theory and finite volume method to update the fluid variables. So the flux plus the cell interfaces cancel pairwise, and the direction turns conservative. But for the magnetic field, on the other hand, we use a so-called constraint transport finite area method and the Stokes theorem. So the magnetic field on the faces is updated by the electric field on edges. And those electric field on edges, by using Stokes theorem, cancel pairwise, so we can ensure that the diff-V is equal to 0 condition is preserved to the machine position if it's set initially 0. So the first extension of and the improvement we recently implement in the MFE code is the high order methods. And we can see why this is important by simply look at the one-dimensional linear direction equations. dq over dt plus is equal to the negative u naught dq over dx. So we all know the solution is very simple. The analytical solution is a traveling wave. So if the U0 is positive, then the wave just go to the right without any deformation. And if the U0 is negative, it goes to the left without any changes. So things is different if we solve the equation numerically. We need to have temporal and spatial discretization. And here I just use a first order method for temporal discretization, and spatially I use the first order Uplink method. And then we do the tail expansion. I will not go through the details, but after all the algebra, the conclusion is that numerically solving the linear direction equation is effectively solving the linear direction equation with the is effectively solving the direction diffusion equations because of the numerical truncation error instead of solving the original linear direction equations. So the numerical truncation error introduces a diffusion error, and mathematically it means that all the wave profiles convolve with a Gaussian. So whenever you have a bulge or the cave, as the time increases, it got smeared anyway. And you won't have the wave structures preserved very well. And here we shows a movie of the linear vector of 4 different shapes. And we clearly see that time increase, all the waves become Gaussian because of the numerical diffusion, and we have no idea what those waves were originally. So basically, it means that diffusion means that we are having an effectively Reynolds number equal to U times L divided by nu, where U is erection terms and nu is the viscosity terms. So it means that numerically solving the system can sometimes be reached to a viscous or dissipative system. However, in the realistic solar or space system, the systems are usually inviscid or dissipationless, which means that the system is of infinite Reynolds number. Using a low order, for example, first order method is having a effective Reynolds number comparable to the grid numbers, which means that if we have n grid cells in one dimension, then effectively we are solving a system of n Reynolds number. And fine structures cannot be formed in a very highly viscous system, which means the system is of a low Reynolds number. So what we're trying to solve is not necessarily what we want to solve, what we get. So the first extension is an improvement is that we decided to use the high order reconstruction method to reduce the numerical diffusion. So the overall process is that we first use a high order reconstruction or the interpolation method to get the cell of interface left and right states from the cell average variables. And then we applied a very aggressive partial total cell method, also using the RFM and the Gamera code for preserving the monotonicity of the solution near the shocks and the discontinuities, and make sure there's no oscillations near the shocks. And more recently, we have developed a improved version of the high order reconstruction method. So the method can achieve to arbitrary high order accuracy and preserve monotonicity in arbitrary orthogonal curvilinear geometry, even with a steep curvature. So now we can kind of quantify the improvement by comparing the low order method with high order method. We know the solution of the effectively we know the solution of the advection diffusion equation we solve. So if we simply solve the square wave equations, we can have an analytical solution in the form of a error function. And then we can compare the solution solving the square wave using the lower order method and also the higher order methods. And we can see by using the first order method, a discontinuity can only be resolved by using more than 30 cells. The second order piecewise linear methods can be resolved by more than 10 cells. While using a high order method and combine it with the aggressive quartz limiter, we resolve the discontinuity with 2 or 3 cells. And we got 100 times improvement in the increasing numerical Reynolds number by using high order methods comparing with the low order methods. We kind of get what we want by using the high order methods. And here we show the two-dimensional linear erection problem of a slot cylinder. On the left is we use a low order, second order method, and on the right we use a high order method. So basically we can see that with the use of high order method, the shape of the cylinder preserves quite well. When the low order method, the discontinuity and the shape got smeared.
A question about that. So if you keep running it,
Mm-hmm.
and obviously the second order method is going to show more fuzz.
Yeah.
Does the higher order method start developing more fuzz as well? I mean, how long
Yeah.
to run it before it breaks down?
Well, for some very aggressive method, it will keep the shape very well even after a long period. But for the method we are using, it actually is the shape will also be smeared as the time because the numerical diffusion is there always. Yeah. Yeah, but relatively the improvement is large, even though there's the diffusion is there. And here we showed an application of MFE simulation of the prominence cavity system. So the simulation is done in a spherical wedge domain. The initial state is a quasi-static corona streamer. And we assume a fixed temperature and adjust the base pressure according to a radial one-dimensional equilibrium relationship, and impose the emergence of a twist flux flow in the lower boundary as a lower boundary condition. And we compare the results using the low order and the high order methods. So on the left is I'll be showing the result using the second order method, which is relatively low order. And on the right, I'll show the result using the recently implemented high order method. Oops, no. So we see by using the high order method, we actually capture a lot of more fine scale structures comparing with the low order method. And also, if we look at the AI image from the different angle, we can actually see the filament bulb structures quite clearly, which cannot be captured in the previous 2018 simulations. And the filament bulb structure is actually consistent with the observation. And probably by looking at the bulb's direction, we can tell the magnetic curvature of the surrounding environment. And a possible explanation for this structure is because of the plasma material is subject to interchange, unstable. So the curvature of magnetic field effectively is having an effective gravity, causing the interchange instability. So the second extension and improvement is implementation of the full sphere simulations. So far the simulations are all performed in a regional domain, and we just simply apply a reflective wall boundary condition or the outflow boundary condition for the angular theta and phi direction. And we cannot model global interactions, which is quite important because the CME event is usually a global expansion. And there are several numerical challenges for us to extending the code full sphere simulations. The first one is the so-called grid anisotropy. We can see that near equator, the cell length in the theta and phi direction is nearly 1. So when we extend the domain to the full sphere, the grid cells near the pole is skinny, that the theta direction is the arc length of theta direction is far more larger than the phi direction. So we have a very skinny cell leads to a great imbalance of numerical diffusion near the geometric axis. And also we have zero phase area along the geometric axis, which is bad for our magnetic field induction equation solver, since we are using a finite area method, but now we have zero area, so we have no idea how to do it. And the most important challenge is the so-called time step limits, that the simulation time step is so small that we actually cannot continue with the simple extension to the global model. So this can be understood by simply looking at also looking at the one-dimensional linear regression problem and the derivation of the so-called CFL condition. So if you use the same discretization, numerical discretization, that the first order temporal method and the upwind spatial method, and put everything into the Fourier space, we end up a numerical scheme with a amplification coefficient G. And the G will be smaller than 1 if the so-called CFL number epsilon is smaller than 1, and epsilon is equal to the time step divided by the cell length. So which means that the so-called CFL number tells us that a numerical scheme is unconditionally unstable if the time step over the cell length is larger than 1. On the other hand, the method is conditionally stable if the time step is less or equal than the cell length. It means that the speed at which the information travels within the computational mesh during one time step must be less than the distance to the nearest mesh element. So basically, it means the time step is proportional to the cell length and 1 over n, where n is the cell numbers. But things got more tricky when we use a spherical grid and try to extend to the full sphere. So the problem happens to the azimuthal direction. So the azimuthal cell length is equal to r times sine theta times delta phi. But when we go to the pole, it actually is effectively equals to the r times delta theta delta phi. So the time step is proportional to 1 over n squared instead of 1 over n for full sphere simulation. Which means that, so for the Thomas cavity eruption simulation, it costs, the regional one, it costs 1 million core hours. But if we simply extend the code to full sphere without any modification, it costs 100 million core hours, which we cannot afford. So the method we use is we implement the in-yang overset grid proposed by the Kagayama. So we use two identical size low latitude overlapping partial grid spherical shell with our theta phi grid with orthogonal polar axis. So the blue one is the in grid and the red one is the yang grid. The axis of the yang grid is pointing to the negative x to the in grid, and the z of the yang grid is pointing to the y in the in grid, and the y of the yang grid is pointing to the z of the in grid. So we have two good spherical shell each covering the 90 degree in the theta direction and the 270 degree in the phi directions. And we have nearly uniform grid avoiding the high latitude region, so avoiding all those grid anisotropy and avoid the zero base area and also the time step limit because we are not going to the pole. So for the implementation, we have the same algorithm and the MPI three-dimensional domain deposition for each yang and in domains. We use the NTI number king point-to-point communication cost between the boundary processors, and also we obtain the ghost zone values by the bilinear interpolation and vector transformation. So here we show the standard quaternion test to verify our numerical algorithm and also the full sphere implementation. So the test is basically a global three-dimensional direction of a few magnetic field loops. So the loop is initialized at a constant center at a constant z plane, a constant z height with a thickness of 0.2 and a radius of 0.5. And the problem is it's quite high beta, so the field loop will be theoretically will be advanced passively, so the shape should be preserved quite well. And another challenge for this test is that actually the loop will go across the in-yang boundary condition. So if the new algorithm is not implemented well, then we can probably see some artifacts and oscillations near the yin-yang boundary. Yeah, but the result is shows that our interpretation is perfect. We don't see any artifacts. And because we use a high order method, the shape of the field is kept well, even there's a continuities. And here we show the global solar wind simulations using a simple dipole magnetic field configuration representative of solar minimum conditions. So the horizontal resolution, angular resolution is 3/4 degree, and the radial resolution is about 7.5 megameter. We initialize the magnetic field with a dipole potential field with a strength of 10 Gauss, and this is the initial dipole field lines, and the profile of the temperature is as a function of the radius of the radial distance. And here we show the 4-panel movie showing the snapshot of the field lines, the radial velocity of the equatorial plane, and also the wildlife images for the Earth view and polar view. So we see that from this simulation, we see the dipole field configuration produce a Helmholtz streamer representing the solar minimum corona, and with the equatorial current sheet and polar corona holes. And we also see at the equatorial plane, there's a very dynamic magnetic reconnection and current sheet drives underneath the somewhat direct jets, resembling the so-called observed super-arcade downflows, usually observed by the soft X-ray and EOV observations. And what I find interesting is that in the heliosphere current sheet, what we get is very similar to what happened in the Earth magnetosphere. So this is a simulation by Mike using the IFN code showing the bursty bulk flow structure in the magnetotail regions. So both phenomena shows a very dynamic inflow and outflow patterns and the reconnection events, even though they are of different spatial and temporal scales. And we plan to make more detailed analysis and comparison between the two phenomena. Also, we examine our algorithm implementation and the scaling efficiency by having more and more CPUs running on these specific problems. And we actually show that the algorithm have a perfectly linear scaling up to 8,000 cores for this small size problem, which means that if we have a 1,000 cube simulation, we probably can have a perfect linear scaling up to 2,000 cores without any problems for the yin-yang global simulations. In the future, we might be using a more realistic observe magnetogram for global CME or the solar wind simulations instead of the dipole simulation, dipole field initialization, which we expect to get more realistic and more dynamic structures. And another future plan is So here we perform a nonlinear alpha wave test for testing the convergence of the codes. So even though we are using a high order reconstruction method to reduce the numerical diffusion, we are having a code that is formally second order converging because the dispersion area is still second order, which is the same as the LLFM code and Gamera code, all having second order convergence, even though using the high order reconstruction method. So the method is to use to correctly distinguish pointwise and cell average values in the finite volume framework, and then we can have a formally high order solver instead of a second order method. Somewhere here, we present the recent development and extension and some of the application of the global magnetic flux eruption in Yang code. And by using high order reconstruction methods, we effectively reduce numerical dissipations and capture more fine scale structures. And recently, we implement the yin-yang overset grid, allowing us to perform full sphere global CME and wind simulations. We wrote a meta paper with a detailed description and a set of standard and non-standard tests of the codes and algorithms, and that's it.
Thank you for this interesting talk. Any questions for Hongyang?
I have a question. As you probably know, the LFM grid and the Gamera grid that are used for geospace studies is a stretched spherical grid. How would you do that with the yin yang grid? Can you stretch it?
Actually, the answer is yes, but so far we only stretch the grid in the radial direction, and we keep the angular direction uniform. But theoretically, you can have a non-uniform grid spacing even in the angular direction. But the requirement is that you need to have the stretching the same for yin and yang. So the yin and yang should be the same.
So I have a question. You said that your new scheme allowed to reduce the numerical diffusion, and I'm probably wrong, but I know that numerical diffusion also helps to inhibit the oscillations of the numerical solutions if you use high order schemes. So my question is, did you observe that in your case, when you use the low diffusion scheme, you have spurious oscillations in the areas where you have sharp gradient of the MHD quantities?
I don't understand. Can you make the question a little bit shorter?
Yeah, do you observe that you have spurious oscillations in the sharp gradients areas when you use lower diffusion scheme?
Theoretically speaking, so when using a lower order method, you get more diffusion and the oscillation should be less. And when using high order method, you got more oscillations because of the low diffusion. Yeah, but in realistic simulations, sometimes those things become opposite and you have no idea what's happening. You need to, yeah, it actually depends.
I also have a second question. Could you please show the slide where you compare two schemes, like, and formation of the filament and eruption?
Yes.
Yeah, I noticed here that in one of the cases, the eruption happened earlier. In which one? In the new scheme or old scheme?
Now, these two simulations are basically similar, but we have several parameters different. So I think those, and actually the simulation domain and is, I think for the right, the this one is a little bit more high resolution because we are using a smaller domain compared with this one. So the eruption time can be different. So they are not using exact the same initial condition,
But if you like, let's theoretically think about that. If it would be the same resolution, same domain, just different numerical schemes, will it be the same onset time for eruption?
It will be different.
Different.
it probably can be
I
different. and-
observe that higher resolution, less diffusivity flares happen later.
Makes sense?
Yeah, probably because with a higher resolution and lower diffusion, you is having a better ability to keep the magnetic energy and stuff.
Thank you.
I have a question. So on the two pieces of the yin yang grid,
Yeah.
are they, I mean, are the grid still that long or something else?
Yes.
It's still that long, I see.
Yeah.
Okay.
You are, yeah.
But just avoid the,
Yeah, so we have two good shells.
You can
Yeah.
pretty much use your old code. You don't have to change your code.
oh, that's,
Or it's the ghost zone changed. Just
it's just bypass that, cut out the
Yeah, yeah.
polar region.
you just
Yeah,
do two simulations basically, but they're parallel. You know,
I see,
all you do is it's the boundary exchange.
I see. And another quick question is why seventh order? Is that a good compromise between, computational cost and order, or is it?
And so for I think we're using seventh order methods, but for MFE we are actually using fourth order methods because MFE is having two ghost zones and 2 times 2 is 4, so we can only go to fourth order, but it's already having a very good improvement by using the partial donor cell methods. So I think that for the fourth order is the criteria after comparing from the first order to up to 10th order. Actually, fourth order is already a pretty good options.
The question, when you use the constrained transport on the yin yang grid, does it strictly conserve diff B even when you put the two grids together, or do you produce some small amounts of diff B out there?
It's conserved in yes, because the electric field is still updated by the magnetic field is still updated by electric field, so it should be preserved to zero.
I kind of have a question at the opening too. When in the overlap region, the yin grid and the yang grid are the coordinate lines are not aligned.
Yeah.
Do they does the energy conserve in the overlap region?
Well, the answer is no. But this is unavoidable even if even you use the this is unavoidable because we are using the MFE code. So let's go back to the first slide. So the equation we are solving is the eternal energy. So anyway, it's not conserved even without yin yang.
Oh, well, I'm not talking about this one.
Yeah.
Say if you get rid of the source terms, then the system generate fluctuations even if we don't have source.
So the only variable that can be conserved is the mass equation because it's written in the conservative form. And for the momentum equation and the energy equation, it's originally not in the conservative form for MFE, so it doesn't conserve the energy and momentum, but it's truncation error, so it should be acceptable. And for many, even for the other codes using a conservative form for the momentum equations, when putting the equation into a spherical coordinate, you inevitably get the geometric sources that is non-conservative. So by using the yin-yang code, by using the yin-yang grid, actually no code can conserve angular momentum or linear momentum. But we believe it's due to truncation error, so we should be safe. Because the sun is not rotating that much in that short time period.
Related, but not quite, in the kind of stitched region where, as Hamnan says, you know, the grids are not aligned. So I mean, you have to have a solution everywhere on the grid. Which do you use, or do you interpolate from one to the other in that kind of overlap region or at the interface?
Yeah, so after each time step, we have the MPMI communication and we do the bilinear interpolation from in to yang and yang to the in to get the boundary conditions. Yeah, and we make the vector transformation to get the vector stuff. Yeah.
I have a question. At the end, you mentioned that the effective, let's say, convergence was like first, second order. Related to what?
This one?
No, at the end, like the last, maybe not the last slide, but the previous.
No.
Next.
Really short the
Okay,
phase
yeah.
wave
Alpha wave,
test.
keep going.
Okay.
The convergence test.
Yeah.
Exactly. So, I mean, that's the convergence test, and you show that the effective convergence that you're having is second order.
Mhm.
Where are you losing? I mean, you said that you lose in the phase and edge construction.
So what do you mean?
So in principle, your scheme is fourth order.
In principle, it's second order. The reconstruction is high order.
Okay.
Yeah, but mainly because the reconstruction is one dimensional, but then the code is multi-dimensional, so we kind of lose the information in the transverse direction, and it causes the dispersion error and restricting the code to the second order.
All right. And the previous test that you were showing, like for instance, the ones rotating, the different shapes rotating.
Yeah.
I bet it was with not a set of equations, and it was like a 2D. I mean, it was a 2D surface and things moving there, and that's why over there you could actually show clear distinction because between the lower and the higher than here.
Yeah.
It's actually different.
Any questions from the online people? And if we don't have more questions, let's thank our speaker again. We'll see you next week.
The stretching, you can do it differently for in and yang.